Okay, is it working now? Can you tell? Okay, all right. Yeah, so if the dual of its minimal free resolution is also acyclic, so the minimal free resolution looks something like this. Each of these Fi's is a finally generated free module. And then here it ends with the ring itself, and this is resolving S mod I. I guess I should say we're at minimal free resolution of S mod I. So then its dual looks like this. Right? And the condition that this is acyclic is saying is that whatever in here is exact. Or in other words, it resolves whatever the co-kernel of this last map is. And if you know, well, the co-kernel is indeed X C of S mod I S in this case. And this also is known as the canonical module of S mod I. But if you're not familiar with this, don't worry, I'm not going to use this at all in the talk. Right, so you can just think of the definition of being perfect as a condition that you take a minimal free resolution, and you take its dual, it's still acyclic. Okay, so I've introduced a parameter here, which is C. So C being the length of this free resolution. So as such, C is the projective dimension of S mod I, just by definition. And the more sort of conventional definition of what it means to be perfect is that this is in fact equal to the grade of I. But if you're not familiar with what the word grade means, you can think that this is actually just synonymous with codimension or height in this particular case. And this relies on the fact that S is Cohen-Macaulay. So some nice fact about the ambient ring allows me to just use those things synonymously. And that's the reason I use the letter C also, is because I think of it as codimension. Okay. So two important parameters, aside from the codimension, that are associated to a perfect ideal are the deviation and type, which I'll now introduce. So the deviation, oh, actually, I'll make one more comment, which is now that I've at least mentioned the adjective Cohen-Macaulay, so if you happen to be more familiar with this adjective, then in this setting, perfect and Cohen-Macaulay are almost synonymous in the following sense that I being perfect is equivalent to S mod I being Cohen-Macaulay. And this uses the, well, this is using the fact that S is regular, and you can prove this using the Auslander-Buchsbaum formula. Right, so if you're more familiar with the adjective Cohen-Macaulay, they're basically synonymous in this setting. All right, so two important other parameters associated to a perfect ideal are the deviation and type. So the deviation, right, so it's measuring how much the ideal deviates from something, and what it's deviating from is being a complete intersection. So complete intersection is the case when the ideal is generated by C elements. Right, so the deviation is you take the minimum number of generators of your ideal, which is the first Betty number, beta 1. So I'll just make a side comment when I write beta I. This is always going to be shorthand for beta I of S mod I, which is the rank of the free module Fi in the minimal free resolution. Or if you want to say this more, I guess, intrinsically, you would say this is the dimension as a vector space of Tor I, S mod I, C. Right. So the deviation is the first Betty number minus the grade. Right? The idea being that if this were a complete intersection, this number would be 0. And the other important quantity is the type, which is T, and this is just the last Betty number. Or in other words, it's the minimum number of generators of the canonical module. Okay. So in particular, there are a lot of families of perfect ideals that are characterized in terms of these numbers that I sort of already mentioned one, which is, for instance, when D equals 0, this is complete intersection. And we abbreviate this as CI. Sort of amusingly, when D equals 1, they're called almost complete intersections. Okay, so just require one more generator than complete intersection. And then when T equals 1, this has a very well-known name. These are the Gorenstein ideals. Okay. But in particular, from the definitions I've given here, you see they're encoded in the minimal free resolution of I, right? The deviation has something to do with how large the start of the free resolution is, and the type has something to do with how large the end of the free resolution is. So sort of the soft question that I want to ask, right, is can we upper bound the complexity of perfect ideals. So as stated, first of all, it's not really clear what I mean by complexity. There could be many different ways you could try and define this. And also, you can probably imagine the answer to this question, regardless of how you define this, would probably be no. But the idea is that, okay, but what if I fix some parameters? For instance, I fix C, D, and T. Can I then talk about the structure theory of such ideals? So fixing C, D, and T, can we upper bound the complexity? And I wanted to give a very particular definition of complexity, which is just the intermediate Betty numbers. Okay, so e.g. the beta I between 2 and C minus 1. I should point out there are, I guess, orthogonal notions of complexity to this, like, in the sense that there are perfect ideals with very small Betty numbers that can be very, very complicated in other senses. But for the purpose of today's talk, I'm going to talk about this. Right. Well, before we embark on this question, maybe I'm kind of curious what people's priors are on this. So let me just give an example. So let's say I fix C equals 4, D equals 2, and T equals 2. So then in this case, a sequence of Betty numbers, which I always start writing as starting from B0, right? This would be 1. So the last F0 is always the ring itself. And then D being 2 and C equals 4 means that the F rank of F1 is 6. And then there's beta 2, and then beta 3, and then the last Betty number is, I'm assuming, to be 2. So then I'm not expecting you to have any justification for this. I'm just curious. Raise your hand if you think you can bound these two numbers. Raise your hand if you think you can't bound these two numbers. So you think you can, or you can't? You can, okay. I mean, is this just a hunch, or do you like have an idea for? That's right. Oh yeah. So let's talk about that also. Like this, like there's another question you could ask is, can you lower bound the Betty numbers? For that, I'm not really going to talk about it much during this talk, but I'll point out that, for instance, okay, when D equals 0, we know what all the Betty numbers look like. Right? So when D equals 0, you have a complete intersection, and a complete intersection is resolved by the causal complex. Right? So in this case, F is iso to causal complex. Which in particular, D equals 0 implies T necessarily is equal to 1, but also that all of the Betty numbers beta I are known, they're just C choose I. Right? And while I'm on this comment on lower bounds, right, so another question you could ask is, can you lower bound the Betty numbers? And a famous conjecture of Brooks summarized independently by HOROX is that these are the lower bounds. And a corollary of this conjecture is that the total Betty number, the sum of all the Betty numbers, will be at least 2 to the C. And this was proven by Walker and characteristic other than 2, and then by Walker and Van de Bogert in general. But here I'm concerned with the sort of opposite question, which is, can I upper bound the Betty numbers, fixing the two ends? Okay. I mean, if you don't have a prior on this, that's fine. I mean, I didn't really have much of a prior on this question either. But let's start by making some basic observations. So this was for this sort of a first trivial observation. Let's look at some other ones. So another observation is that there is one linear relation on all the Betty numbers, which is that the alternating sum is equal to 0. Right, so observation, sum minus I to the I, beta I is equal to 0. And how can you see this? Well, there's various ways you can see it. Perhaps the easiest is that since this is well, it has positive grades, so it at least contains some non-zero divisor, you localize by inverting that non-zero divisor, and your resolution becomes split exact. And then this just boils down to checking the same for a split exact complex, but that's just linear algebra. So various ways you can see this, but this is true. But given this, it means the question is kind of trivial or maybe even vacuous for small values of C. Right? So for instance, for C equals 2, well, the question is vacuous because there are no intermediate Betty numbers. And in fact, the D and T are closely related, right? So C equals 2, and the resolution just looks like this. You just have R to the T, and then R to the 2 plus D. And I guess I'm using S, so I should be consistent here. Right? But then the fact that the alternating sum is 0 tells me that, what, T plus 1 equals 2 plus D, so T equals D plus 1. Right? And then there's also just no other Betty numbers to talk about. Right, so for c equals 2, this is vacuous, the question. And then for c equals 3, the question is trivial because of this observation. Right? Because in this case, the free resolution looks like this. You have a type, and then something to be figured out, and then 3 plus d, the deviation, the s. But then the alternating sum being 0 implies that this must be 2 plus d plus t. Right? So again, this is sort of trivial. Right, so the first interesting case is c equals 4, for instance, examples like this. Right. But within c equals 4, right, so first interesting case, let's not first start with that. Let's start with something simpler. Let's start with, say, c equals 1 and t equals 1. C equals 4 and t equals 1. T equals 4, t equals 1, which means the Betty numbers look like this. So I have 1, and then something, beta 3, beta 2, and then the deviation is, well, it is whatever it is. It's 4 plus d, and then s. All right, so maybe a question for the audience. Can I say something about these unknown Betty numbers in this case? Or what's the lower bound then? That's right. So we have two observations here, right? So one's that we know about the difference because of this equation, right? But also because of this very special property that when t equals 1, the dual of the resolution is not just resolving anything, it's actually resolving something that's isomorphic to S mod I itself, right? Because it's a Goranson ideal. This is a special property of Goranson ideals. So because t equals 1, we have that F dual is isomorphic to F. So that means that beta 3 is just 4 plus d. And then from the other observation, we deduce what beta 2 is. Right? So because of this, we have that beta 3 is 4 plus d. And then beta 2, let's see if I do this right, it should be 6 plus 2d to make the alternating sum 0. Yeah, that's right. So it's exactly. So I'll briefly mention that later. But indeed, that itself is an interesting question. And for example, when c equals 3 and t equals 1, they know that d has to be even, for instance. Uh, so I don't believe there's a complete characterization in general. Okay, so this is another case where actually just knowing the three parameters nails down the entire resolution. All right, so that was fixing t equals 1. Let's look at the other way, which will say c equals 4, but d equals 1. So in this case, I have a resolution that looks like this. S to something, S the beta 3, S beta 2, and then S5, right, because deviation is 1, to S. Now the question is, can I bound beta 2 and beta 3 in terms of t? So this question is a bit more subtle, but it turns out to be actually very closely related to the previous question. And I'm going to use this opportunity to introduce a tool that's very prevalent throughout this theory of looking at structure theory of ideals, which is linkage. So go back over here. All right. So we have this ideal I in S, and then we let alpha 1 through alpha c in I be a regular sequence, or in other words, this is a complete intersection ideal contained inside of I. So contained inside of I, i.e. alpha 1 through alpha c and I is a regular sequence. Right? And then we define the ideal J to be the colon, which just as a reminder, this is by definition all x in the ring such that xi is contained in, alpha 1 through alpha c. And you should think of this as geometrically being akin to subtraction in some way. And if you look at like the varieties, this will be like you're taking the variety defined by this and subtracting in some sense the variety defined by I. Okay? So then, I haven't defined yet what linkage is, but if it happens, so there's a condition, so if it happens that the reverse is also true, which is that I is alpha 1 through alpha C colon J, we say I and J are directly linked, and we write I sim J like that. Okay. So despite this, well, this is it's not an equivalence relation because it's not transitive. It is, and it's also not reflexive either, but it is symmetric just from the definition. For the purpose of today's talk, I'm restricting to perfect ideals, and I'll just point out there's a very nice fact about perfect ideals. This goes back to Peskin and Spiro, basically. It says that if I is perfect, then this is automatic. So you just take any colon ideal with a using a regular sequence contained in I, and then the ideal you get is linked to I. Okay, but the main result I'm going to use about this is, since I'm mostly concerned with free resolutions, is a result that says you can write down a free resolution for S mod J if you're given a free resolution for S mod I. This is a result that is attributed to Ferrand, although it appears in Peskin and Spiro's 1974 paper. So this is Ferrand in 74. Okay. It says that, so let F be as written before, the free resolution of S mod I. So let me write this again. So F is 0 FC F1 S resolving S mod I. Okay. Then if you have this regular sequence, alpha 1 through alpha C contained in I, what you can do is you can take the causal complex on this regular sequence, and then make a comparison map from the causal complex to F. And this last term here is isomorphic to S itself. This is some comparison map phi. And the statement is that if you take the cone of this map, and then you take its dual, then this resolves S mod J. Now let me write down explicitly what this is, or at least a couple of terms of it. So what this is, at this end, you have S, and the preceding term you have FC dual plus K. Okay. And then at the end over here, you have F2 dual plus K dual. And then you have, well, these can cancel, right, in the when I write down the mapping cone. So then I'll just have, at the very end here, F1 dual. But notice, however, this is not claimed to be a minimal free resolution, and it is quite possible that when you write down this comparison map, the vertical maps here may be non-zero mod M. And being non-zero mod M would imply that when you write down the mapping cone, this will be not minimal. In particular, if you take your alpha 1 through alpha C to be part of, say, a minimal generating set of your original ideal I, then this map here will be a split inclusion, so there will be a lot of non-minimality already here at the end. Okay, but what does this tell us? This tells us that if we're able to upper bound the Betti numbers for some family of ideals that I belongs to, then just from this construction, we can get an upper bound on the family of ideals that J belongs to. And also, what does this have to do with what I was saying before? Let's consider the case that your ideal I had let's say your ideal I had deviation 1. Okay? So this is isomorphic to S to the C, and this is S to the C plus 1. So you take a regular sequence among the minimal generators, and this will be a split inclusion, and then when I perform the evident cancellation at the end here, I'd be left with an S1 at the end. So if you input an ideal with deviation 1 to this construction, you take a minimal link, which is a link where the regular sequence consists of minimal generators, then the output is a Goranson ideal. Or symmetrically, you could do the same thing the other way around, which is input a Goranson ideal and then you get a almost complete intersection. So what does that mean? It means that from the fact that we have an upper bound, or in fact, we don't just have an upper bound, we know explicitly what beta 2 and beta 3 are here, we can get an upper bound for almost complete intersections. So let me do that now. So if this resolves S mod I, then let's say I is linked to J for some Gorenstein J. So let me write down the resolution of J. It will look something like this. So S1, the Sn, the S2n minus 2, Sn to S. This is resolving S mod J. And then I'll make this construction. So the comparison map. So the Kozel complex in this case has ranks 1, 4, 6, 4, 1. Right? I make a comparison map like this. Then if I write down the dual of the mapping cone, then I get a resolution of S mod I, which may not be minimal, but I get a resolution which looks like this. So S, and then S5, and then Sn plus 6, and then S2m plus 2, and then, well, these cancels at the end here, I just have Sn. So let me remind myself what my objective is. My objective is to try and bound these middle two Betty numbers in terms of this last one here, right? This may not be minimal though, right? So this may not be the actual Betty numbers of S mod I, but where can the non-minimality be? So if I assume that this is a minimal Fourier resolution of S mod J, then these will certainly be 0 mod M. And since I'm taking, well, this is also going to be 0 mod M. So the only possibility of units appearing in the differentials are in these vertical maps here. But in particular, well, there can't be one here because I'm assuming that my deal is almost a intersection. So here is here or here. So at one extreme, this is basically as non-minimal as possible, which is to say that in this case, this entire map here is a split inclusion. And what that means is that in that extreme, the minimal resolution of S mod I, this would be an S to the n minus 4. Right? But that's the lowest that this could be. So given this, so I'm basically trying to infer what I can say about this. So this may not be the minimal free resolution of S mod I, and I'm trying to infer what the minimal free resolution of S mod I might look like. So at one extreme, I'm trying to see so these numbers might be actually smaller in the minimal free resolution based on how non-minimal these two differentials are. Now, one extreme, this one is as minimal, let's say, and this one is as non-minimal as possible, and that means that this is a split inclusion. So in that extreme, what you get is that at this end, you would actually have S to the 2n minus 4, and then S to the n minus 4. So the largest difference that you can get here between the Betty number here and this one is 10. So what this implies here is that beta 3, or no, beta 2 rather, right, beta 2 is at most t plus 10. But then once you have beta 2, you can figure out beta 3 from that alternating sum condition. So I will point out, though, that this is a weaker conclusion than this. This is just a bound. And if you go the other extreme, you can show that beta 2 is at least t. So you see it's very coarse bound here that beta 2 should be between t and t plus 10. But it's, as far as I'm aware, still unknown what actual range values within that range can actually be assumed. Yeah. Directly linked to a complete intersection or just in some? Great. Yeah, so that's going to be sort of the goal of this, and that's where I'm sort of headed. So I'm happy that you preempted that question. But it turns out that, so the short answer is going to be no. Yeah. All right, any questions about the examples that I've done so far? That's right. So, yeah, this is completely general. Yeah. So far, not yet. Yeah. In fact, the characteristic 0 is only going to come at the very end where I state that something is proven in some case. Yeah. Okay, I guess in the next example I do, I'll assume characteristic not 2. But, yeah. Okay. So maybe I'll leave this for the time being because I'm going to use this somewhere later. Right. So we've handled c equals 4 t equals 1 and c equals 4 d equals 1. So the next case of interest will be c equals 4 d and t equal to 2, which was the sort of starting example that I asked. But we're not going to do that yet. I'm going to first continue looking at the t equals 1 case because of this nice self-duality, right? Somehow, like when t is 1, we have half as many Betti numbers to figure out. So maybe let's try and stick with that case for a while and see what we can say. So let's move on to c equals 5, still fixing t equals 1. So c equals 5, t equals 1. And let's say, let's also fix d, because it turns out that if you don't fix d, this is already going to be quite hard. But then as was pointed out earlier, right, there's a result of Kunz that says that d actually cannot be equal to 1. So first of all, d equals 0 is a complete intersection, not interesting, we already talked about that. And the d equals 1 is not possible. So d equals 1 impossible, but maybe I'll just write this. This is a more general statement, right, which is dt equals 1, 1 is impossible by Kunz. Right, a paper that's titled Almost Complete Intersections Are Not Gorenstein, exactly ruling out this possibility. So the first case of d that could be of interest here is c equals 5, d equals 2, t equals 1. Right. And here I'll just tell you what's known, which is a theorem of Lopez, who's a student of Baron Döllritz, is that assuming characteristic is not 2, but I mean, I'm not going to write it because I'm basically assuming characteristic is 0 throughout, that the only, actually, okay, I'm doing things slightly out of order here. I forgot to mention one thing, which is, yeah, so this being the linkage class of linear section is something that I'm going to use in this statement, so I'll define it now. So we say that I is in the linkage class of a complete intersection, which is abbreviated as saying I is Lichy, if there exists a sequence of links I to a complete intersection. And it's a fact that, well, okay, I'm sort of assuming that I is perfect, but even if you don't assume that I is perfect, being Lichy is stronger. So an ideal that is Lichy is necessarily perfect. And that's just because perfection is carried across linkage. Okay, so what Lopez showed in his thesis is that if, assuming these parameters, a Lichy ideal with the above parameters has f one of the following. I guess beta, I'll just write the Betti numbers. Either you have beta is 1, so the fact that it's deviation to Codimension 5 means that the next number will be 7. Right? And then it's Gorenstein, so then it's something, something, 7, 1. But the only two known possibilities, in fact, the only two possibilities, assuming your ideal is Lichy, are that this number is either 16 or 21. Okay. And actually, he does more, of course, a lot more than this. He characterizes what these ideals are. These are the hypersurface sections of codimension 3, Gorenstein on 5 generators. So I guess double hypersurface section, because this is codimension 5. And then these are the Hünicke-Ulrich examples. Which I'm not going to define here, but there are some examples constructed from some skew matrix on a vector. Okay. So I should also point out that in the case of odd codimension and Gorenstein, the linear equation that the alternating sum is 0 is automatically satisfied, so it doesn't really give us any extra information beyond already knowing that this is self-dual. So like a priori, you could have thought that the middle two numbers would be arbitrarily large, but in fact, the only two known possibilities are this. And while I'm at it, I'll just make a comment, which is that there are no, you might be wondering, like, how restrictive is this? And the comment is that there are no known non-Lichy examples of with these parameters, with parameters C, actually not just fixing C, but with dt equal to 2, 1. Okay. So depending on what your prior is, you might see this as conjecture, all such ideals are Leachy, or you might take this as a hunt to try and find a non-Leachy example. What's that? Over any ring, even if you assume the ambient ring is a polynomial ring, this is not known. No. So along this, still continuing this d equals 2, t equals 1 case, let me tell you a more general result, which is a result of Hünecke, Ulrich, and Vasconcelos in 96, which says that if for parameters b, t equals 2, 1, and assuming that S mod I is generically Ci and unobstructed. So if you don't know what this word means, just know that it includes the case of Leachy, so e.g. Leachy. Okay. This is some deformation theoretic condition, says that T2 is 0. Okay. But in particular, it includes the Leachy case. What they do is they explicitly construct an exact sequence like follows. From S to the C plus 3, choose 2, to S to the C plus 2, to S resolving S mod I. Okay, so what does that mean? It means that, well, I don't know this is minimal, but at least I have some candidate differential D2. So this implies that under these assumptions, so in particular, we have that beta 2, which is also equal to beta C minus 2, is at most C plus 3, choose 2. But what if I plug in, say, C equals 5? Then this is 8 choose 2, which is 28. But what you see here is that we don't actually know any examples where these middle guys are 28. So it seems in the case of C equals 5, this is not sharp, and that the largest middle Betty numbers here known are 21. Great, so I'll answer that question right now. So what about the next value of C? What about C equals 6? So for C equals 6, assuming this, right, if you have a Leachy ideal, for instance, then, so let's say C dt equals 6 to 1. Right, so then what do the sequence of Betty numbers look like in this case? So I have 1, then 6 plus 2 is 8, and then something, 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 8, 1. Okay, but if we believe well, okay, this is a theorem, but it's a theorem with some conditions. But so take these assumptions, then for an ideal satisfying these assumptions, this will be at most 36, this will be at most 36, and then from the condition that the alternating sum is 0, you can deduce the middle one is at most 58. Okay. So then I'll just say, a fact, then I don't know how to attribute this to, maybe Macaulay too. There is an ideal attaining these maximums. Right, so with beta 2 and beta 4 equal to 36 and beta 3 equal to 58. Right. Okay, so let's do one more value of C. So let's say C dt equals 7 to 1. So in this case, this result does not nail down all the Betty numbers. Right? And again, since C is odd, the alternating sum condition doesn't really tell me anything beyond what I already know from Gorenstein. So what I have here, I have 1, 9, and then assuming these hypotheses, this is less than 45, then something, something less than 45, 9, 1. right? And while I'm at it, let me just write back down the other case that I sort of teased at the start, which is C dt is 4, 2, 2. And this was beta equals 1, 6, something, something, 2. Right. So with the examples that I've shown you thus far, you might be inclined to think that maybe we can just always bound the intermediate Betty numbers. But it turns out that for these two cases, you cannot. So proposition, actually, I'll call this. There exist, in each of these two cases, or these two cases, there exist ideals with arbitrarily large intermediate Betty numbers, the blanks here. So I'll very briefly sketch the proof, or how do you go about showing that these exist. So the idea is to pick a suitable, so take a suitable homogeneous ideal in the polynomial ring with, say, the standard grading. Right, so I want to take at least enough variables to have, so n is at least c. And then what you do is you define ij to be a direct link to ij minus 1, where these constitute a regular sequence of maximal degree among the minimal generators of ij minus 1. Okay, so I will say that, like, so what happens is that if you pick a good choice of starting ideal, then you could use this map income construction that I described to you before to write down a resolution of each linked ideal in terms of the previous one, although of course you don't know if this is minimal or not. Right, so it may happen that the resulting ideal actually has smaller Betty numbers than what you write down from the map income here. But that's where the homogeneous, the fact I'm taking a homogeneous ideal comes in, which is that since I'm working with a homogeneous ideal, this whole picture is graded. So although there may be cancellation, I can sort of bound the amount of cancellation, right? Because if you're in the graded setting, the cancellation only occur when the map is going between the same degree, right? So basically, I mean, this, I don't claim, I mean, there's a lot of work here that I'm not showing you. That you basically find a pattern, show that you can actually lower bound, even assuming maximal cancellation, the number of the Betty numbers in the middle, and that will show that, so, and then that the limit as n goes to infinity of these, say, beta 3, I guess, in this case, of S mod in is unbounded. But of course, this is not going to work for an arbitrary choice of I0. There's like some special choice of I0 made here that makes this work. But the striking thing is that, like, if in these cases, for instance, this one and this one, no matter what I you take here, you're not going to make this work because of these bounds. And any ideal that's constructed in this manner, I guess I didn't really tell you, but the ideals constructed in this manner, I start with something Leachy, so they'll also be Leachy. Okay. And which one? Yeah, this one's also Leachy. Right. If it were not Leachy, then I would have a violation of this. Okay, so it remains an open question whether there are non-Leachy ideals with these parameters. Okay. Any questions so far? Right. So, like, that's a great question. Like, why is this weird dichotomy in behavior? Like, why is it bounded up to this point and then suddenly becomes unbounded? Right. So that's what I want to explain next. And I sort of tease this in my abstract, which is that all of this has something to do with representation theory somehow. So, but actually, before I get to that, I'll just tell you like how these examples are constructed. Like, there's a sort of systematic algorithm for constructing the ideal that attains this, and also the ideals that do this. Okay, so I'm going to let S be a polynomial ring and some n variables, where n is at least C. And then I'm going to define the set PC of ideals in S as follows. So it's going to be basically the smallest set that's closed under the following two things. So it contains all ideals generated by C linearly independent linear forms. We just say a complete intersection generated by degree 1 things. So any L1 through LC is an element of this set, where a degree, so sorry, L1, LC independent linear forms. And the idea is that the set is going to be closed under all homogeneous linkage, but under some sort of more restrictive homogeneous linkage, which is the following. This is a bit technical, so get this down. All right, so suppose, so if I in PC with minimal free resolution, let's say the last shifts here are minus B, C, J, and then here I have minus B1J, is this resolving S mod I? So I'm going to define an integer k, which the exact formula here is not really important, but I'm just going to write it down for completeness. There's two ways of defining it which are the same. So if you look at these expressions, you might be first thinking that why on earth should this be an integer? And indeed, in general, if you take an arbitrary ideal, there's so no reason for this to be an integer, but it turns out for ideals in this set I'm defining, this will always be an integer. And then also define lambda I to be k plus 1 minus each shift here in the first module. And I define mu I to be, yeah, I hope I got this right. This is, I think, k plus c minus 2 minus b c j. But again, the exact formulas here are not really important. All you have to know is that there is some special integer associated to this ideal. And then what I require this set P to be closed under is that if I take a particular type of regular sequence, namely, suppose I is generated by H1 through some Hn, where the degree of Hi is equal to lambda k plus 1 minus lambda I, and alpha 1 through alpha c is a subset of this. So each of these is in here is a regular sequence. Then the colon ideal is required to be in PC as well. Okay, so this is very technical, but I want to just say what this is really saying. This includes minimal homogeneous linkage. So if you take an ideal that's in the set, you take any regular sequence among the minimal generators, that will satisfy this. What this is really saying is that if you restrict yourself to minimal links, then you can't really get more complicated examples in some sense. Like you can't make the deviation or type increase if you do that. So you need to allow for some kind of non-minimal linkage. And what's being said here is that if you do non-minimal links, the elements of your regular sequence, which are not minimal generators, have to be in the special degree k plus 1. That's really what this whole thing is saying. So for instance, if you start with a complete intersection like this, which by the way, you can check that for complete intersection, this integer k is equal to 1 by either of these two definitions, then the requirement is that you can either link by, well, this regular sequence, which would be very boring, it'll just give you the unit ideal, or you do a non-minimal link, but if you do a non-minimal link, the non-minimal elements must be quadrics. That's the restriction. That's right. So this construction is very specific to a graded ambient ring. So I'll just say right now that the ideal that, for instance, realizes this bound and also the ideals that are used in that construction come from this family of ideals. They're constructed in this manner. But what's sort of special about this family of ideals, I'm going to write down a conjecture and then tell you in some cases in which this conjecture is known to be true. So conjecture one. So for I in this set PC, the Herzog class of S mod I. And if you don't know what this means, so this means basically this ideal up to deformation, but in particular, this means for all things in the same Herzog class, they have the same Betti numbers. So these intermediate Betti numbers, S mod I, are determined by lambda and mu, or in other words, determined by the first shifts and the last shifts. So this is a very surprising observation, and it's not proven in general, except in some cases. But it's saying that if you know you have an ideal in this family, you know the shifts here, you know the shifts here, then you know what all the middle Betti numbers are. And then if you assume this, then you can define an assignment from ideals in this set to or more specifically, from pairs lambda and mu that are realized by ideals in this set to Herzog classes of these S mod I. And the claim then, the substance of the next two parts of the conjecture is that this map is a bijection, at least for Lichy ideals. So the first thing that's surjective, which is that every Lichy ideal is in same Herzog class as some, every grade C, so codimension C, as some I in PC. And again, if you don't know what this means, just know that as a consequence of this, it would follow that every possible list of Betti numbers realized by Lichy ideal is realized by some ideal in this set. That's what this is saying. And then finally is the claim that this map is injective, which is that if I1 and I2 in this set have different lambda mu associated to them, then they are in different Herzog classes. Although I will say that this notion of Herzog classes is a finer classification than Betti numbers. You can have ideals in the different Herzog classes but have the same Betti numbers, for instance. Okay. So now let me tell you about when these are known in. So 1, 2, and 3 are known for C equals 3, but unfortunately for C equals 3, the question of intermediate Betti numbers is not interesting. But then also 1 and 2 are known if this sort of funny thing is true. So I'm going to draw it now. And this is finally leading towards what I was hinting at before. So I'm going to draw this T-shaped graph with arms of length C minus 2, D, and T. Okay. And these are known if this graph is a Dynkin diagram. And this is not a free coincidence. In fact, the way these are proven relies on some representation theory coming from this case. So I'm not really going to explain what exactly this representation theory is, but I want to point out what's special about these compared to the previous examples. So we try and draw the diagrams in these cases. Right, so if I draw CDT 6, 2, 1, which was this last one here that we actually had a bound, right? The diagram you get in this case is 2, 3, 4, like this. Okay? And this is a diagram E8. Whereas if you go to 7, 2, 1, then you get E9, I guess, as some people call it, but this is not a Dynkin diagram. And also, what about this case? So before we talked about these, we looked at, for instance, C dt equals, say, 4 and then d1 or 4 1t, for instance. So what do these look like? So this is a bit strange because in this case, actually, right, you have this arm here of length d, which could be very long. So for large values of d, this is going to be a Dinkin diagram. But even then, you can fix the Betti numbers. But this is just going back to what I was saying early on in the beginning, which is that the measurement of Betti numbers is only one measure of how complicated ideals get. And if you believe this, then in particular, well, okay, I didn't write it here. But it turns out that for large values of D, even though the Betti numbers are known, the ideal is going to get very, very complicated. But in particular, what's up with C422, or C dt is 422, this gives this diagram, but this is not a Dinkin diagram. This is one of the affine Dinkin diagrams, E61, not Dinkin. So in some way that I certainly don't have the time to explain here, the fact that this is not a Dinkin diagram has some connection to the fact that there are arbitrarily complicated ideals with these parameters. So I think I'll stop there and just take questions. Where in CDD you can draw a square like X, and then that is of same type, then it is, yeah, what is your expectation like? So the expectation is okay, well, I'll tell you the part that is actually proven, which is that if you draw this graph and it is a Dinkin diagram, then there are only finitely many Herzog classes of Lichy ideals with the given parameters. In particular, you can use this to generalize the result of Lopez that I mentioned before, that said that his parameters 5, 2, 1 is the case of E7, with one sort of configuration of the arms. And he showed that there were only two families there. But more generally, if you ever get a Dinkin diagram, there's only many families, and they can be related to somehow Schubert varieties. In the case that the graph you get is not a Dinkin diagram, the expectation is that there should be infinitely many families. However, the obstacle to proving that is that we need some technical results from representation theory that doesn't seem to be known, actually. Yeah. What if it's, oh, I mean, when I say finite or infinite, that also, okay, this algorithm, all right, so what I'm saying here in particular includes that. If it's infinite, then it's, of course, not empty. What happens when it is d equals 1, t equals 1? What is the... So when d equals 1, t equals 1, you get a Dinkin diagram. You get the diagram dn for some value of n. And then if you go through the machinery, you can enumerate all of the ideals that you expect to get in that fashion, but it turns out to just be 0. You don't actually get any. Yeah. But I will say, though, like, a priori, even if you did this and got the count 0, that doesn't tell you they don't exist. That just tells you Lichy ones don't exist. Right? So it's still, like, not complete. Yeah. That's right. I mean, the conjectural part, you could try and say an arbitrary characteristic, but particularly I say these are known for C equals 3. This is relying on characteristic 0. Yeah. Great. Yeah. So I would be very, very happy if someone could locate either a proof of the statement that what I need is basically this. If you have some Dinkin diagram, you can look at a homogeneous space associated with this, and you look at Schubert varieties in the homogeneous space. And it's a well-known classical result that arbitrary unions of Schubert varieties is any such arbitrary union is linearly defined. Like you can define it scheme theoretically as the vanishing of Pfluger coordinates. This is also known in the infinite dimensional setting. However, the caveat is that we actually need the statement for opposite Schubert varieties rather than Schubert varieties. In the finite dimensional setting, the distinction between opposite and not opposite is superficial because they're really just related by the action of like the longest element of the Weyl group. But the infinite setting, they're very different beasts. So in the infinite setting, there's literature that says unions of Schubert varieties are linearly defined, but what we need is that unions of opposite Schubert varieties are linearly defined, and we cannot locate such a statement. Because the proofs for the unions of Schubert variety thing are usually by induction on like the dimension or something like that. So it doesn't really work for opposite ones. By this perspective, well, there will be some hope for lower bounding based off of the, say, Lichy ideals, but these lower bounds I think are already very well known. So, right, the problem is that if you have an arbitrary perfect ideal, then you could attempt to try and localize it to make it a Lichy ideal, and this process of localization can only drop the Betti numbers. And this seems like a viable strategy unless you run into a case where the perfect ideal cannot be localized to a Lichy ideal, except for the unit ideal, basically. So then, well, what can you do then?
Not, let's think again.